Okay, so let's take a look at the first problem involving a prism. Okay, so that's problem number 1. So we've got the following prism. Okay, glass prism with a right angle there. Okay, and then there's an incoming light ray, like so. It gets refracted. Okay, when it's inside the prism, it's refracted, and when it leaves the prism, it's refracted again. So we have something like that. So let's just fill in the normal so we can see what's happening. So we've got a normal going like that and a normal going like that. So we see that when the light ray goes from air into the glass, it's refracted towards the normal as expected. And then when the light ray exits the glass, it is refracted away from the normal as expected. Okay, so let's say that the refraction index of air is 1. Okay, that's pretty standard to do. And the refraction index for glass is going to be 1.5. Okay, now just note this 1.5, don't take it as given. In your tests or quizzes, it might be something like 1.48 or something like that. Okay, so always take the number that is given in the test. Okay, don't take this number as given. Okay, now this angle here is 45 degrees. And what we want to work out is this exit angle, let's call that theta 4. We want to work out what that is. Okay, so this first angle of entry or angle of incidence, we can call theta 1. The angle of refraction inside, we can call that theta 2. The second angle of refraction as it's going out, angle of incidence as it's going out, we can call that theta 3. And then we have the exit angle of refraction, theta 4. Okay, if I'm losing you at any point, please just shout out and then I can explain again. Okay, so we need to find out what this theta 1 is. Okay, that's not given to us. But what we do know is that this incidence ray is parallel to the base of the prism. So we can use alternate angles to use a different color. If this angle is 45, then this angle is also 45 by alternate angles. And secondly, we know that the normal is 90 degrees to the surface. So if the second angle here in green is 45, then theta 1 must also be 45 so that it adds up to 90. So theta 1 is equal to 45 degrees. Okay, so that's good. Next, we can then find theta 2, theta 3, and then theta 4. So let's start with theta 2. How do we find theta 2? We're going to have to use Snell's law. So N1 sine theta 1 is equal to N2 sine theta 2. Okay. So we want to find theta 2, right? So sine theta 2 is equal to N1 over N2 sine theta 1. So theta 2 is going to be arcsine or sine inverse of N1 over N2 sine theta 1. Okay, we can just plug in the numbers. We know that N1 is going to be 1, N2 is 1.5, and theta 1 is 45. We worked that out. Okay, so just using your calculator, we end up with 28,1 degrees. Okay, as expected, because we wanted this light ray to move towards the normal. So if the incidence angle was 45, we expect the outgoing angle to be less than that. Okay, which we do have. So that's just a quick little check that you can do. If you expect the light ray to move towards the normal, you should be getting a smaller angle. Okay, which we do. Next, we need to find theta 3. Okay, how do we go about doing that? Well, what we can do is recognize that this line, the line of incidence here, if we extend that and we extend the normal, we have ourselves a little Z shape. So let's just fill that in. So over here, we've got the Z kind of shape with the two horizontal lines being parallel. Now, if they're parallel, it means that this inside angle here is equal to the other inside angle. Okay, so we've just used our alternate angles there. So what is this inside angle? Let's put that in blue. So this part here in blue, how do we find that? Well, we know that this total angle here, this angle here, we know that that angle over there is going to be 45, because theta 1 is 45. So this opposite side here, this must also be 45. Okay, so we know that theta 3 plus theta 2 must equal 45. Okay, that is from vertically opposite angles. Okay, so I've just extended those lines to make that cross shape. Then the angle over here, this angle here, must be equal to this angle here. Okay, because they are vertically opposite. Okay, but we know what theta 2 is, so we can find theta 3. So theta 3 is going to be 45 degrees minus theta 2, which we worked out as 28,1. So theta 3, just check that is 16,9 degrees. Okay, so we've got theta 3. So theta 3 now becomes the new angle of incidence. So since that is the new angle of incidence, we can find theta 4, which would then be the angle of refraction. So let's do that on the side here. So N3 sine theta 3 is equal to N4 sine theta 4. Okay, and we want to find theta 4. So sine theta 4 is going to be N3 over N4 sine theta 3. So theta 4 is going to be the arcsine or sine inverse of N3 over N4 sine theta 3. So that's going to be the arcsine of N3. That is the index of refraction on the inside. So that's the one with glass. And N4 is on the outside. So that's air. So we're going to have 1.5 over 1. Sine of theta 3, we just worked that out. That is 16,9. Okay, put that in your calculator, and we get 25,6 degrees. And let's just do a little check. We expect the angle of refraction to be bigger because it needs to move away from the normal. Okay, the inside angle was 16,9, so the refracted angle should be bigger. We get an answer of 25,6. It is bigger, so we can be pretty sure about this answer here. Okay, so we get theta 4 is 25,6 degrees. Okay, so you see that since this light ray refracted multiple times, we just solve the problem in steps. So we do the first part where it refracted, the second part where it refracted, and then we can calculate our theta 4. Okay, and at each step, we just use Snell's law because we have to handle the refraction. Okay, any questions on this first problem? Okay, so it's not too bad. It's just using Snell's law a couple times because of the multiple refractions. Okay, if you do have any questions, please just shout out or post it in the chat and then I can read it. Okay, let's take a look at the next problem on fiber optic cables. Okay, so this is problem number 2. We're interested in how fiber optic cables work and if there is a limit to the use of fiber optic cables. So let's say we've got the following cable. it extends onwards to the right. So we're not too interested in that part. What we're interested in is this entry point to the fiber optic cable. So where the light enters. Okay, so just say for generality that the light enters like so. Okay, at some angle θ1. Okay, we want to be general because we're not too sure yet at what angle the light enters the cable. But what we do know is that as soon as the light enters the cable, it's moving from air to glass, and so it's going to be refracted. We also know that it's going to be refracted towards the normal. So it's going to bend something like this. Okay. Now, what we want is to have total internal reflection, right? Because if we don't, then this light ray is just going to exit the cable. We don't want that. We want this incident ray on the inside to be such that the light ray is then bent back into the cable, or it's reflected back into the cable. So it's going to do something like this and continue. And then it will carry on bouncing in the cable. Okay, so let's just put some angles here. So the incidence angle is θ1. Let's say this angle here is θ2. We need to draw our normal. So let's say this angle is θ3. Okay, and then we want it to reflect inside. Okay, so the first thing we need to handle is this part over here with the reflection. Okay, so what we want to find is the critical angle for glass and air. Okay, because we've got glass on the inside and air on the outside. Okay, air, we can take the index of refraction to be 1. Glass, we can take it as 1.5. Okay, so don't memorize these. They will be given in the test. Okay, so we need to find the critical angle. Remember, for total internal reflection, the incidence angle needs to be at least the critical angle. In other words, the incidence angle must be greater than or equal to the critical angle. Okay, so let's work it out. So for total internal reflection, there's one condition that we need to have, and that is that the incidence angle, in this case is θ3, must be greater than the critical angle. If it is equal to the critical angle, you know that it just moves along the surface. Okay, we don't want it to move along the surface. We want it to get reflected back into the glass. So it must be strictly greater than. Okay, this is the condition. Okay, so we need to work out what this critical angle is. Okay, so how do we do that? Well, that's just a special case of Snell's law again. So at this point here, where the light ray is bouncing off the glass, we can use the Snell's law to work out the angles. So N3 sine θ3 is equal to N4 sine θ4. Okay, so remember, we want this θ4 to be 90 degrees. That's when we get the critical angle. So this θ3 then becomes the critical angle. Okay, so we're going to have sine θc for the critical angle is going to be N4 over N3, because sine of 90 is 1. So the critical angle is going to be arcsine of 1 over 1.5. So we've got air on the outside, glass on the inside. Okay, and then you can just check on your calculator. This gives us a critical angle of 41,8 degrees. Okay, and this will be universal for any glass to air transition. Okay, so it doesn't matter what the thickness of the cable is or the length of the cable. It's universal for glass to air transitions. So just keep that in mind for later. Good. So we can write the condition for total internal reflection. as theta 3, this inside angle over here, must be greater than theta c. Okay, must be bigger than the critical angle for this to all work. In other words, theta 3 must be greater than 41.8 degrees in this special case. Okay, so that part's done. What we want to do now is calculate theta 2. Okay, how do we go about doing that? Now, remember that this is called geometric optics. So there's a lot of geometry going on. What we can do is extend this normal line to the other normal line and produce a right angle triangle. Something like that. Next, we know that theta 2 plus theta 3 plus the 90 degrees must be 180 because of the sum angles triangle. So that allows us to find theta 2. Okay, because we know that theta 2 plus theta 3 must be 90. Okay, if you add it to the other 90, you get 180. So if I add theta 2 on both sides, I'm going to get theta 2 plus theta 3 is greater than theta 2 plus 41.8 degrees. Okay, so I've just added it on both sides. But theta 2 plus theta 3 from our previous argument is 90. So 90 degrees is greater than theta 2 plus 41.8 degrees. Okay, we just take that over to the other side and we get 48.2. Okay, if you just subtract it over, is greater than theta 2. Okay, that's the next bit of information we got. So again, if we go back here, for total internal reflection, theta 3 must be greater than the critical angle. And that is the same thing as saying theta 2 must be less than this angle. Okay, it's the same condition. We're just phrasing it differently so that we can end up with theta 1. Okay, so we've got this angle now, or a bound for that angle. Finally, we can look at the theta 1, theta 2 transition. Again, it's a refraction because we're going from air to glass, so we can use Snell's law. So we do that. So finally, we have N1 sine theta 1 is equal to N2 sine theta 2. Okay, we're just using Snell's law because we're dealing with refraction. Okay, so we just put in the values that we know. We know that N1 is going to be 1 because we're going from air. So sine theta 1 is equal to N2, which is 1.5 sine theta 2. Okay, 1.5 because we're going into glass. Now, this is an equality. So we've got this being equal. However, in our previous workings, we had inequalities. So this was an inequality. So what we need to do is manipulate this equality so that we can introduce the inequality. Okay, because we're working with bounds. So we're saying theta 1 must be less than some angle or bigger than some angle. We're not looking for an exact angle. Okay, so what can we do? Sorry, let's go back to the pen. So note that. Okay, we can start off with this inequality that we had here. Theta 2 is less than 48.2. Okay, we know that. We worked that out before. Now, if we take the sine on both sides, it preserves the inequality. Okay, because sine is monotonically increasing. So we have the sine of theta 2 is less than the sine of 48.2 degrees. Okay, so let's just draw a little picture just to explain that. So remember, these angles are going from 0 to 90. Can't go more than 90 because we're measuring from the normal. So if this is 0 and this is 90, sine looks something like that, up to a maximum of 1. So if, let's say this point here is x, and this point here, let's call that y. If y is less than x, in other words, it's on the left-hand side, if we look over here at this point being the sine of y, and we look at this point up here, this point being the sine of x, then if y is less than x, then the sine of y is also less than the sine of x. Okay, because we've got this going on here. Okay, so this is for monotonically increasing functions. So it's increasing like this. If y is less than x, then the sine of y is also less than the sine of x. It preserves that inequality. Okay, which is good because this is what we wanted. We wanted sine of theta 2. Okay, so we've got a bound for that. Okay, so we multiply both sides by 1.5 because we're trying to get this. So 1.5 sine theta 2 is less than 1.5 sine of 48,2 degrees. Okay, good. So 1.5 times the sine of theta 2 is less than 1.12. Okay, so it's less than 1.12. And we know that sine of theta 1 is equal to this. So sine of theta 1 is equal to 1.5 sine theta 2, which is less than 1.12. So sine of theta 1 is equal to 1.5, sorry, the little times there, 1.5 times sine of theta 2, which is less than 1.12. Okay, so sine of theta 1, let's just highlight that here. So we can have sine of theta 1 is less than 1.12. Now, for what values of theta 1 is this satisfied? Well, we can have all theta values. Satisfy this relationship. Okay, because sine is always less than 1.12. Okay, because we can write this as 1 plus 0.12. Okay, it's always less than or equal to 1. So if we make this bigger, then it's always satisfied. In other words, you can have any angle of incidence and still get total internal reflection. So this shows us that you can have any angle of incidence, okay, the theta 1 angle of incidence, and you would still get total internal reflection for the fiber optic cable. However, it's very important to note that this is a property of the air-glass transition. Okay, it's not a universal property, because remember, in all our calculations, we assumed it was going from air to glass. In other words, from n equals 1 to n equals 1.5. It doesn't work for all ratios. Okay, if this were plastic, you might get something different. Okay, so with that in mind, we've got our first homework problem. Okay, and I encourage you to do these homework problems because these homework problems tend to turn into test questions. Okay, so just keep that in mind. So homework problem. For which ratios of N1 over N2. So in this example, we looked at air to glass, but let's just say air to something else. So let's make this more specific and say 1 over N2. So the top one we just take as air, but we don't know what the bottom is. N2 is free to be something else. So for which ratios of air to some other substance does this not hold? Okay, so that's part one. In other words, you don't always get total internal reflection for any angle. And part two, what is the bound or bounds on theta 1 in that case? Okay, so this is the homework problem. And remember what I said, these homework problems tend to become test question problems. Okay, so part one, for which ratios of 1 over N2 does this not hold? So we see that in this case, if we look at air to glass, it gives us something that is always bigger than 1 in this case. And if it's always bigger than 1, then it always holds. So when does it not hold? Okay, what ratio limits the value of theta, theta 1? And part two, if this theta 1 is limited, what is the bounds on it? Okay, maybe there is some critical angle of incidence where you get total internal reflection and other parts where you don't. Okay, so I want to know, how does theta 1 depend on this N2? Yeah, so that's for part two. Are there any questions about this homework problem? Okay, let's take a look at the third problem. Okay, sorry, just give me a second, please. Okay, third problem. So we've got a block of glass or a slab of glass, like so. Okay, so this is glass inside. And we've got air outside. We've got an incoming light ray, like so. And it's coming in at an angle of 30 degrees. We know that it's going to be refracted. We also know that it's going to be refracted towards the normal. So it's going to do something like this. Next, it is going to exit and move away from the normal, right? Because it's going from glass to air. So it's going to move away. Okay, and you can check this on the side. But the incoming ray or the incident ray is going to be parallel to the outgoing ray. Okay, because it gets shifted in the glass, but as it exits, it remains parallel to the incoming ray. So we can just extend this line like so. Sorry, that's supposed to be parallel. And we can extend this line like so, and those two lines are going to be parallel, okay, because of the double refraction going on there. So the question is, if this glass block is 10 centimeters thick, so this is 10 centimeters, and we know that the incoming ray is at 30 degrees, I want to know what is the separation distance between these parallel lines. Okay, what is that shift or separation distance there? Okay, so how do we go about solving this problem? Well, it's a bit more complicated than the usual diffraction problems, refraction problems, but it's not too much of a problem. Okay, so let's just zoom in here to the point of refraction here. So we have an incoming angle at 30 degrees. It is then leaving at an angle, let's say theta 2. Okay. Now, if that is theta 2, let's call this other angle here theta 3. Okay, I'm just labeling the diagram so we can work with this. Okay. And what we want to find is this distance over here between the parallel lines, that's d. Okay. So what we can do is use a bit of trigonometry to put in some triangles so we can work some things out. So the first triangle I'm going to draw like so. We know this is a right-angled triangle. Okay, we know that the adjacent is going to be 10 centimeters. Okay, because that is the thickness of the block. The hypotenuse, we don't know what that is, so let's just call it h. And the opposite, we don't know what that is, but we don't really need it. Okay, what we want to do is calculate this hypotenuse h. Once we have this hypotenuse h, we can then calculate d. Okay, so a little bit of trig. H cos theta 2 is going to be 10 centimeters. Okay, just a bit of trigonometry there. Okay, but we don't know what theta 2 is. However, we can find theta 2 because we know that is the angle of refraction from this incoming light ray. So we can use Snell's law there. So n1 sine theta 1 is equal to n2 sine theta 2. Okay, we want theta 2. So a bit of rearranging. Theta 2 is going to be sine inverse of n1 over n2 sine theta 1. Okay, we know all of these. This is going to be sine inverse. Air is 1, glass is 1.5. The incoming angle was 30, so that's sine of 30. Just put that in your calculator. We get 19,47 degrees. A quick little check to see if this makes sense. The incoming angle was 30 degrees. It's going into a more optically dense medium. We expect the angle to get smaller. Yes, the angle did get smaller, so we can be pretty sure about that. Okay, if we got a bigger angle, then we should be worried. Okay, but that's fine. Next, we can find the hypotenuse using that bit of trig that I explained. So h cos theta 2 is going to be 10 centimeters. Okay, just a bit of triangle work there. So h is equal to 10 over cos of 19,47 degrees. Okay, just put that in your calculator. We get 10,61 centimeters. Okay, which makes sense because the hypotenuse should be larger than the adjacent side. Okay, not by much here, but it is bigger, so we can be all right. We can be sure that that's correct. Okay, so we've got h. Now that we've got h, we can find the side length d. That's going to be another triangle. So let's just put that in green. We are now looking at this triangle in green. Okay, so we've got this green triangle. Here is another 90 degree. Okay, so we've got theta 3, and the opposite side is d. The hypotenuse is h. Okay, we want to find d. Okay, but first we need to find what this angle θ3 is. Okay, how do we go about doing that? Well, we know that θ2 plus θ3 must be 30 degrees. Because if this angle is 30, then this angle, the whole angle, must also be 30. Okay, again, because of those vertically opposite angles. Okay, so let's work that out. So finally, how do we find D? D was the opposite in that green triangle. So we write H sine θ3 is equal to D. Okay, that's the opposite. So H sine of 30 degrees minus 19,47 degrees is equal to D. We know what H is. We just work that out here. So D is equal to 10,61 times the sine of 30 degrees minus 19,47 degrees. Just put that in your calculator. We get 1,94 centimeters. Okay, so that is the shift in the light rays. So it came in at 30 degrees, and then the exiting ray is shifted by this amount, the 1.94 centimeters, but it remains parallel. So the exit ray and the exit ray going out and the entering ray coming in, they remain parallel, but just shifted by a bit. Okay, that shifting amount is 1.94. Okay, any questions on this one? Okay, so you're out with this. Okay, cool. And then the second homework question, let's just go through that here. Okay, number 2. So in this picture here, we had a fixed length L and a fixed incoming angle of 30 degrees. Okay, so the angle of incidence was 30 degrees. My question is, what happens if we change that angle? How is this shifting distance dependent on the angle of incidence? Okay, so for a fixed L, okay, so the size of the block remains the same. How does our shifting distance D, so remember this was the shift, how does the shift depend on the angle of incidence? That was θ1. Okay, so that's part 1. Part 2, what does the graph look like? Okay. In other words, θ1, if we go back here, θ1, we can have it being 0 degrees. In other words, it is hitting the glass block directly. So the angle from the normal is 0. We expect D to be 0, right? There shouldn't be any shift if it's going in directly. If it's going in at some angle, then we expect there to be a shift. What happens as this angle goes to 90? What happens to the shifting? Is there a maximum shift? What happens there? Does the shift go to infinity? What goes on? Okay, so what does the graph look like? In other words, D versus θ1 for 0 less than or equal to θ1. I shouldn't say, right, less than or equal to theta 1, less than 90. Okay, so it might not be exactly 90, because then the light ray is just going tangent to the surface. We don't want that. So just before 90, what happens? Okay, so some questions to ask yourself. Is there a maximum shift? D. I don't know. You're going to have to look at the graph and see, is there a maximum shift that you can get? Okay, so that's homework question number 2. All right, any questions on this homework problem? Okay, any questions on the work covered for this week? Okay, so you've got your mid-semester break coming up. So technically it's a break. However, I will be available should you have any questions. So please just put them on the group and I can answer them. Okay, and then when we get back from the mid-semester break, we will move on to the reflections from curved surfaces. So if you have a spherical mirror or some general concave mirror, how do those work? Okay, and then after that, we will look at lenses and how they focus light. Okay, so any questions before we go? Okay, cool. So give these homework questions a try. I can almost guarantee that they will come out in some form for the test. Okay, so you won't get all those very easy questions for the test. You'll get some applications like this. So looking at, sorry, where's it? Here we go. How fiber optic cables work, how lenses work, stuff like that. So it won't be like those TUT 1 questions. Those are too simple. Okay, I'll see you next week for lecture 3. Bye, everyone.